This is an example of an AC analysis problem in Circuit Tutor at level 3. And this will be the second type of problem on that level, since there are actually two different types of problems. So let's first just show an example. This is again at the hard or level 3. And as with the other problem on this level, this is a superposition problem. The difference here is that we have a total of 3 sources rather than 2 in order to compute our desired sought quantity, which in this case is this voltage V0. Notice this problem is being given to us in the phasor domain, as we can see from the complex value of the impedances and the fact that the capacitance and inductance values are in ohms, not in farads and henries, respectively. Also, we notice that the source values are all given as phasors, that is, complex numbers, rather than being functions of time as they would be in the time domain. So the first thing you always want to do in a superposition problem is to see if any simplifications can be done by combining elements in series or parallel prior to killing sources, because doing it once at the beginning is much more efficient than having to do it each time you kill a source. Then you'd have to do the same thing 3 times, which would be rather tedious. So we notice that these 2 passive elements are in series. However, one of them does have a sought voltage, which prevents us from combining them directly, because we would lose that sought voltage. But what we can do instead is to convert that sought voltage to a sought current, which is being done here. Using a simple Ohm's law type of relationship between V0 and this new current I've defined with the passive sign convention, which is I0. And having done that, then we can eliminate that sought voltage, and now we can get it at the end just by using this auxiliary equation that we've generated here. So now we are allowed to combine those 2 elements in series. So the 4 and the negative J5 just add up to give us 4 minus J5, which is the value of the Z1 down here, that generalized impedance. And we do change the type of symbol because that's no longer either a resistor or a capacitor. It's a general impedance that's a fully complex number. And then we look and see, is there anything else we can do? And unfortunately, no. There are no other elements, passive elements that are in series or parallel, and no sources in series or parallel. So we cannot do any further simplification. So now it's necessary to do the superposition, if that's the method we want to use to solve this problem. So one thing we need to remember is that when you have more than 2 sources, that when you do superposition, you want to have only one source active at a time. If you had 2 sources active in each child circuit, then you'd basically be double counting the effect of each source, which we wouldn't want to do because that wouldn't give us the correct answer. So we want to count the effect of only one source acting at a time. So we have to kill 2 sources here. In this case, we've kept the I2S active, but we've killed the I1S and the V1S sources. And remember that when you kill a current source, you want a 0-valued source to replace it, which means 0 amps is the same as an open circuit. So that's been simply deleted from the circuit, whereas the V1S needs to be changed to a 0-valued voltage source or short circuit, so that now appears as a short in the circuit. And now we have just the one current source active. So scrolling down now, we do notice that in that circuit there are 2 elements now in series because of the killing of the sources that were not in series before. So we can combine those very easily by adding their impedances. So that's being done here. And adding 4 ohms to 4 minus J5 just gives us 8 minus J5. So that becomes the impedance now we call Z2 to distinguish it from the previous impedance Z1. And now if we look at the circuit, we say, oh, this is actually just a current divider because we have a single node pair. There's one node here, and then the other node is there. And so now we can just use the current divider formula directly, which is done down here. And so remember, this is now labeled I0 prime because it's only a portion of the complete I0 due to all 3 sources. So it's been automatically labeled for us I0 prime. If you're doing it on paper, you have to remember to put those labels on so that you know what it is you're calculating. So I0 prime, we have the value of the current source, which is 9 angle 75 degrees amps. And then remember that with a current divider, you always put the impedance whose current you don't want in the numerator. In other words, that would be the J6 ohm here. Let's see. Well, that would be over here, I'm sorry, in this form. So this is actually, well, there's different ways of doing it. So this form would put the J6 in the numerator and put the sum of the impedances in the denominator. That's one way of doing it, which is correct. You could also put the admittance in the numerator. In that case, if you're using the admittance, you would put the admittance of the element through which the current is in fact passing. So then you would have the value of Z2, and so you'd have to take the reciprocal of 8 minus J5, and then you divide by the sum of the admittances. So that is algebraically, if you just cross multiply, that's algebraically equivalent to this expression. And so you can use whichever form you like, or you could compute that admittance directly and then just put it in here. This is just an evaluation of that, basically. And of course, these are now Siemens, because remember that admittance is measured in Siemens, whereas impedance is measured in ohms. So you could use any of these different methods to get the answer. It just shows all three for completeness. And also we have to do check on the polarity, because here this current source sends charge going from here down to here, which will then return through here, and then some of it will go through here. Now notice that the charge going this way is going to travel opposite to the defined direction of I naught prime. That means we will need a negative sign in the current divider. That's why we have a negative sign in all three expressions here. That's to take into account the correct polarity. And it's very, very important to remember that, because if you get the polarity wrong, of course, your answer will be very, very wrong. Okay, then we go down, and now we keep just one of the voltage sources active. So I don't have the original circuit here, just convenient, but this is killing the other two sources. So now this is keeping only the V1S source active. And now we look at this and say, well, this is pretty easy because it's a single loop, and we can, and it's turned off the two current sources, as it notes here. So we can just combine those elements in series by adding their impedances, and so that's just been done here, putting it into a single impedance, Z2 it's called now. And remember, this current is now called I naught double prime because it's due to the second source. And then we can just use the relationship that the current is the voltage divided by the impedance. So we have the voltage of 2 angles 0 divided by the impedance 8 plus J1. But again, we always have to check polarity, because that'll come back to bite us every time that we don't check it. So here we see that we have the positive side of the voltage on the side where the current is entering the impedance, and the negative side is on the side where the current is exiting the impedance. So if you remember, that corresponds to what we call passive sign convention, where the current is entering the positive side of the voltage, which in this case is the voltage supplied by the source. So that means that we will have a plus sign in the V equals IZ relationship. So we use this formula as opposed to this one. So that's why there's a plus sign there. But again, if I naught double prime had pointed the other way, or the voltage source had the other polarity, then we would have needed a minus sign. And so it's very important to check that. Then we just compute that on a calculator. It gives us the value of I naught double prime using the complex number features of our calculator. And finally then, we do the third child circuit, where we have the I1S independent source active, and we've turned off I2S and V1S. Remember, we turn off I2S by setting it equal to an open circuit, or zero-valued current source, and we change V1S to a zero-valued voltage source, which is equivalent to a short circuit. So now we have this circuit to analyze, and once again, we look for simplifications that are now possible that wouldn't have been possible originally. And we notice that we have two impedances in series, so we can just add those very easily to make it into a single generalized impedance, which would be 4 plus J6 here. And now this has the form of a single node pair circuit. There's one node there and another one there, so that is a current divider since it has a current source. And we can just use, again, the standard current divider as we did with the other current source. And once again, there's several different ways of doing this, but we put the value of the source to one angle 165 degrees. And then if we want to use the impedance, we put the impedance of the other element in the numerator, and then the sum of the impedances in the denominator. Or if we want to use admittance, then we use the admittance of the element of interest divided by the sum of the admittances. And those are algebraically equivalent to each other, as you can check. And then you could also use admittances already calculated, which just basically does it in that form. Now, in every case, however, we again have to check polarity. That P word we've got to worry about. So here, this current source sends charge from here over to here, which then will return partly through this way and then partly through this way. And when it returns here, you notice it's going to be opposite to the direction of I naught triple prime, which is what we are now denoting the portion of I naught that's due to this I1S source. And because that's going opposite to that direction, then we need a minus sign on all three of these formulas, whichever one we choose to use. Of course, we don't really need all three. I'm just showing that for completeness. And then the final step would be to take the values of I naught prime, I naught double prime, and I naught triple prime and simply add those numbers together using the superposition principle that says you can consider the effect of each source separately as long as the circuit is linear. And remember that circuits with only ideal resistors, inductors, and capacitors, those are in fact linear circuits in the AC domain. So we can add that up, and then just doing that on a calculator, we'd get this value. We have to use the auxiliary equation, however, to get back to the original SOT variable, which you remember was V naught. And so we just multiply this result here, this phasor, by 4 ohms, which will put it into volts, and that's the final phasor value for V naught. And then we do the inverse phasor transform using the value of omega, which is given here, which is 8 kiloradians per second, or 8,000 radians per second. I've just written this out, 8,000 here. And then the phase angle is that of the phasor. So that completes this example. So now let's work an actual problem to show you the details. So here's a new problem. We see that in this case we got 2 current sources and 1 voltage source. That will vary from problem to problem. And so let's look and see, first of all, if we can do any simplification. And immediately we see that we have 2 impedances in series. So it's much simpler to do that now, or at least a little bit simpler. I mean, here it's pretty easy to do that anyway, but let's just do that now so we don't have to do it 3 times. So J1 plus negative J8, obviously that would be negative J7. Remember that we add impedances directly in series, just like we would do if they were resistance values. And then this one we have to change to a short circuit because that no longer should contribute to the impedance here. And so, and of course, if you change it to an open circuit, it's like you're saying neither of those things was there in the first place because the resultant would be dangling, which would have no effect on the circuit. So that wouldn't make any sense. So it has to be changed to a short circuit. So we check that, and that is correct. And now we check to see if there's any more that can be done here. And unfortunately, I don't see any other elements that can be combined because none of the other passive elements are in series or parallel. None of the sources are in series or parallel, so those cannot be combined. And so basically, we have to say we're done for now. And notice that we did not need any SOT variable auxiliary equations here because we didn't change the SOT variable. So now we're going to kill sources. And remember that we need to turn off 2 at a time here. You want to have only 1 active at a time. So I'm going to change this current source, for example, to an open circuit. And I can just do that by deleting it. And I'm going to change this one to a short circuit, which I could do with the right-click menu and change it to a short if I like. Or I could also have clicked up here. And now that's done. We're done killing the sources. Now don't try to start simplifying. Like, for example, you may say, oh, I want to combine those now. You're not allowed to do that in the source killing mode. You have to go out of the circuit editor and come back in simplification mode just because it's not expecting you to do that right now. So we're going to go out of the source killing mode, and then we will go back into the circuit editor in the simplification mode. So that would be simplify circuit. And now let's combine the 9 and the 1 ohms. Of course, that just gives us 10 ohms there. And that will not affect this SOT current I naught prime because the same current exists in both of those resistors at the same time. So combining them will be just fine. And we change the one we don't want to a short. And it's easier, of course, to do that with this one than it is here. If we're going to do it here, we would have to move the SOT current down to here, which is an extra step and probably not necessary. So let's check that. And now if we look at it, we're basically done simplifying. We could simplify more, but let's just use the current divider formula. It's probably just as easy as doing more simplification. So now we have a single node pair, 1 node here, 1 node here. So we're going to use single node pair analysis. In other words, current divider. And we need a current, a SOT branch current, so we'll select that and write that type of equation. And this will be the I naught prime. It's already been primed for us, but if you're doing it on paper, be sure to remember that. And again, you can use any of these terms that you like. If you want to just enter the numerical value right away, you could do that, but you'd have to calculate it first. So I'm just going to do it with this as my favorite type of term to use. So let's do the current source value is 6 angle 180 degrees. And then when I'm using the impedance ratio, I need to put the impedance of the other element in the numerator. Because remember that current takes the path of least resistance, and if we put the impedance of this element, that would potentially contradict that statement. So, okay, so we have negative J7 in the denominator, and then the other impedance also, which is just 10. So that's a fairly simple case. Now we also need to check what? Polarity. Remember, we always check polarity. So this current source sends charge from here to here, which then will return going this direction, and that's consistent with the direction of I naught prime. Some, of course, will go this way. And because that's consistent, we need a plus sign here. So we are correct to have a plus sign, but remember, about half the time, you're going to need a negative sign there. So you always want to check polarity if you hope to get the right answer consistently. Okay, so let's check that. And that's correct. And that's the only equation we need, so we'll click No More Equations. And now we need to enter a numerical value of that, which we'll compute on a calculator. So let's get the calculator now. And very importantly, this I'm using my TI 84 Plus emulator, but it's similar for 83 or 84. If you have an 89, it's actually a little bit simpler than using this one. But the general procedure is much the same. So I want my answer here in polar form, so I want to make sure that I'm in polar form here, or polar mode rather, here for the output. If it said real there, I would for sure have to go into the mode and change that. So normally you go into this mode menu and make sure that you've selected that down here as to which one you want. And you can also set the radian or degree mode, and I want it to come out in degrees here, so I've chosen the degree mode. So everything is already set up for me. And so now I simply evaluate this. So I'll put my 6 angle 180. Now, the easiest way really is just to type that as -6. But I will show you how to do it with the degree. So we have 6 times, and I could put a little exponent, and then I'd have to put I, really I pi would be the answer, or I pi over 180 times 180. But what I'm going to do is take this variable that I've predefined, this e variable, which I've defined as little e to the I pi over 180, and raise that to the power 180, because that's another way of doing this. And that way I can use degrees directly in my calculation without having to put in the conversions in the argument of an exponent. So remember, this is the variable e, not the built-in e, which is based on Neperian logarithms. So I predefined that, as I've shown in some other tutorials on complex numbers. And also, well, in the introductory tutorials on paper, and also the other videos. Okay, so we have that, and we multiply that times negative J7, so times parentheses negative I down here times 7, and divide then by a sum of, well, it's just really 10 minus I7. So I'm going to go I7 using implicit multiplication, which is permitted, either with real or complex numbers. And that should be the entire expression, so I click enter. And now I have the result directly in polar form because I had worked in the polar mode, so I can just copy that over here. So I have 3.441, and the phase angle will be my 100 and, well, let's call that 125 degrees, or 125.0, whichever. And that is correct. So I've finished analyzing with a single source. Now I have to kill sources again to analyze with the for the effects of the other two sources. So let's go back into the source killing mode. We've already done the simplification that we could do. and that's preserved here. So we've already determined that of the I2S source, so we certainly don't want to consider that one again. That's the 6 angle 180 degree source. So let's kill that one for sure. We'll again change that to a 0 amp source, which means basically to delete it or change it to an open circuit. So I can press the delete key, for example. And then the other ones, it doesn't matter which one I kill. Let's just do this one now and delete that as well. And so now we've left one source active. Remember, superposition with 3 or more sources, you have to have one active only. Actually, with any number of sources, you have to have one active at a time. Okay, so we're done with that. And again, don't try to simplify the circuit while you're in source killing mode. It just won't allow you to do that, and it'll give you an error message if you try. So we exit the source killing mode, and now we'll go into the simplification mode just to simplify that down a little bit, make it slightly easier. And so since these impedances are all in series, we can simply add those values, which we can do in our head. And I'm going to have to, well, I notice that I do have a sought current on one of those, but that's going to be the same current in all 3 elements. Therefore, that's not going to stop me from combining them directly, because that will not affect the value of the sought current I not double prime. So I will just keep the one that has that variable, because I'd otherwise have to move the variable to a different element, which I could do, but there's no real reason to do that. So I'm going to have basically 10 minus J7 is the sum of those 3. So I enter 10 minus J7. And notice it's turned it red. That indicates there's an issue. And the issue is that that's now a complex value which is not compatible with the resistor symbol. So we need to change that element to a generalized impedance, which I can do by clicking over here. And now that got rid of the red type that was alerting me to that problem. And then I'll change this to a short, and I'll change this to a short. Remember that when you're removing impedances in series, you always change the ones you're not keeping to shorts, so that you have a total impedance of just this combined value. So we'll check that combination. And that is correct. And so we're done editing now. We've done all we can do. And so now I have both single node pair and single loop. Generally when there's a sought current, I think it's better to use single node pair, so we'll do that. And we're trying to find a sought branch current. And so we have I naught double prime equals, and we could just put in the value here if you want to compute that directly. So let's just do it that way for once to illustrate that method. So we'll use this term, but then we have to go on our calculator first and do the computation. So this is going to be, now again, we do have to watch out for polarity, so we notice that we have the positive side on the side of the impedance where the current is coming out, and the negative side where it's going in, so that's actually active sign convention. So we need to remember that it's not V equals IZ here, it's V equals minus IZ, or I is minus V1S divided by Z1. So we have to make sure we get that negative sign in there. So I'll just put a -7 as a simple way of doing that. I could write 7 angle 180, but that's more complicated to write. So I'll just write -7 divided by our impedance Z1, which is 10 minus J7. So I have to put that in parentheses, of course, because it's just because of order of operations in algebra, as you presumably are familiar with. So 10 minus I7, close parentheses, using implicit multiplication there for the I and the 7. And that should be correct. And again, that's in polar form, which is what we wanted. So I was in polar mode here. So I can just enter that directly now. And this will just save me a step, basically, by doing it like this. So 0.5735. And then the phase angle here is -145.0, or just -145 is good enough there. And we'll check that. And that is done. And then we have everything we need, so we just say no more equations. And now we don't have to enter a value because we already entered the numerical value. So now it wants us to analyze again for the effect of the third source. We've done it due to I2S and V1S. Now we're going to do it for the third source. We have to go back into source killing mode. And the sources we don't want are the ones we already considered, which is I2S. So let's turn that off. That's the 6 angle 180. So we'll remember that changes to an open circuit, so we'll delete it. And then the V1S we've already considered. That's a 7 angle 0. So that then we'll get rid of that by changing it to a short circuit. And then we're done. And so we are done killing sources. And then, once again, we have two things in series here. So now we can go back into the circuit editor, this time in the simplification mode. And remember, we can't do that in source killing mode. We have to do it in simplification. So now we can just add those two impedances together. So I'll replace 9 by 9 minus J7. Because remember, impedances add directly in series, just like resistances do. And then we'll change this to a short circuit. And notice that this is also a red value here. And that means that this has to be changed to a generalized impedance because you can't have a resistor with a fully complex value. Only a generalized impedance can have that. So we'll change the proper symbol, which you'd also want to do if you're doing this on paper. Just use a correct notation. And then we can check that combination. And that is correct. And now we do have a single node pair circuit, so that's sufficient to quit editing. I mean, we could continue, but let's not bother. And we'll do single node pair analysis to use the current divider here. So once again, this is the current divider. And so we're interested in the SOT branch current. And so we have I naught triple prime, which is that current, is equal to, and again, we could enter it various ways. Let's do it this time, just to illustrate something a little bit different. So now we have I1S, the angle, that's 5 angle 30 degrees. So I'll enter that. And since we're taking the reciprocal of the impedances here, or basically using the admittances, we want the admittance of the element of interest now, which would be the Z1 goes in the numerator, which is the opposite of what we do if we're using this term. And this is actually probably the more logical ways to use admittances, but it's just that we don't often express things in terms of admittance as often as we use impedance. So here we'll put the Z1 value, which is 9 minus J7. And then we'll also put that in the denominator, 9 minus J7. And then we put the other impedance here, which is just 1. And then we can check that. Oh, and I forgot, after lecturing you about polarity, that's what happens when you don't check polarity, is you get an error. So again, I forgot to do this. The current through the source is actually going from right to left here. And that means that it'll go back going this way, and that's opposite to the direction of I naught triple prime. So we need to have a minus sign there for sure. Otherwise, we'll get the wrong answer. So now we check that. This time it should work. And we have that. And now we're done entering equations. So now we would need to enter a numerical value for this. Now, this is where probably the other form would have been a little bit better in terms of evaluating on a calculator. This one's actually a little bit more complicated, but we can do it. So we'll come over here to our calculator and okay, that's interesting. So let's take the minus 5 angle 30. So we're going to go, let's see, I'm going to put a minus, well, I think I need to do, I believe that with parentheses, otherwise I'm not sure that's going to work correctly. So we have 5 times, I'm going to use that big E that I defined previously, that variable, which I can raise to the 30, and that basically is using the polar form there. And again, if you haven't defined this variable big E, which is little e to the I pi divided by 180, then you would have to write all that out here, which would be a little bit more tedious. So I'm just using my shortcut that I like to use there, and close the parentheses there. And then, and really, let's just cross multiply this to make this simpler. So if we cross multiply this, we're going to have a 1 in the numerator. And we did, of course, didn't really need to do that. I just did it. And then we're going to have a parenthesis there, and we're going to have 1 plus 9 minus j7, so that'll be 10 minus j7. Which we have to enter as I7. And that should be equivalent to what this was. It would be rather tedious to enter that exactly as written, so I'm just doing a shortcut there. And then we enter that into a form, and that is already in polar form as we want, so 0.496. And then the phase angle is negative 115.0. We'll check that, and that is correct. And now we're just going to use the superposition principle. So we have these three currents due to each of the three independent sources. Remember, you don't use superposition with dependent sources normally, only with independent sources. And so what we need to do is simply add those three values together. And by convenience, I already have them here, but remember that I cannot use this form. That won't work. So I'm just going to go up and grab the original expressions, actually. So I'm going to grab that plus that plus that expression, because those have the correct format for the TI calculator, and click enter there. And then that computes the sum of all those things. And so that will be 3.366. And then the phase angle will be 141, we'll call that. And we'll check that. Now, if you're wondering how do you look at complex numbers and tell if they're correct, well, you could think about vector addition. You could draw a little plot if you want to see roughly how those add. With three of them, it's a little hard to visualize that, but it could be used to tell you if your answer is reasonable or not. So we'll check that, and that is in fact correct. And then the final step is to convert this back into the time domain, or do the inverse phasor transform. Now we already have omega here, so I won't need my calculator. Basically, and ignore the straight text, that's just from my video capture program here. Has a little trouble with this. So this is 3.37, and the omega value is 60 kiloradians per second, so that's 60,000. And you cannot use a metric prefix in this text box at this time, so just enter 60,000 there. And then the phase angle is the 141 degrees. And remember, of course, if you're doing this by hand, you always want to make sure you have that time variable in there. If there was no time, this wouldn't be a function of time, and you would be doing something that would basically be nonsense. So we have to make sure we always have the time in there. It's being supplied for you, but don't forget that that's there. And of course, the units always need to be supplied. So that would be amperes. Okay, so that completes the problem, and remember that you could always request a detailed explanation if you were unsure about anything you'd done here. And so that would show you all the steps involved in doing the superposition exercise. And then we could just scroll down and review any of that, similar to what you'd have in an example. So that completes this problem.